Okay, so now we're going to talk about something we touched on before, bomb calorimetry, based on similar principles, excepting that this technique is usually used for determining the enthalpy of combustion for organic compounds, usually compounds containing carbon, hydrogen, maybe oxygen, maybe some other elements. But basically, organic compounds are the ones that are usually used in this particular situation. So, as stated here, there are some reactions that simply cannot be carried out in the simple low-tech coffee cup calorimeter. So, in the case of other compounds such as organic molecule or organic compounds, we can use a bomb calorimeter, which is what is have here. I think I went through this discussion before in terms of explaining how it works. I won't go through all of it again, but basically what's happening is that you burn your substance here inside the bomb, the steel bomb, and the heat is transferred to the water outside, and you record the temperature. And basically, the Q of the reaction will be equal to the Q of the calorimeter, which can be calculated based on the amount of water present, the initial and final temperature after the reaction is completed. Now, one thing I did not mention when I described this earlier is that the contents inside here is pressurized with oxygen, all right? And as a result, the reaction is carried out under constant volume conditions because there's no change in the volume inside here, all right? So therefore, the Q of the reaction will be equal to the minus Q of the reaction, will be equal to the heat change for the calorimeter, which will be equal to delta U. If you remember a couple of slides back, we talked about the fact that for a constant volume process, the change in the heat of the process of a system would be equal to the change in internal energy. All right. However, we need to recognize that the change in internal energy is not necessarily the same thing as the change in delta H, but it can serve as a good approximation, all right, to delta H. Now, that's all we're going to say about this, because what I really want to get to is a discussion of this law, Hess's law of constant summation. And basically, Hess's law deals with the fact that, well, let me get to Hess's law first and then talk about the example. So Hess's law says if an equation can be expressed as a sum of two or more other equations, the enthalpy change for the desired equation is the sum of the enthalpy changes of the other equations, all right? So basically what they're saying here, and that is covered in this sentence right here, the enthalpy change of a reaction is the same whether or not the reaction is carried out in one step or through a number of steps. So this is just basically another way of saying Hess's law, all right? So what this law is saying is this, and let me get out of this here and get my writing pad. Okay, so basically what Hess's law says is that if you have a reaction going from A to B, or let me just say A to C, but you can also go from A through an intermediate B and then get to C. And let's say delta H1 is the enthalpy change for that step, A to B. For B to C, the enthalpy change is delta H2, and for A to C, the enthalpy change is delta H3. So what Hess's law is saying is that the total amount of enthalpy to go from A to C is the same, regardless of whether or not you go through one step or, in this case, two steps through an intermediate. So basically, we can write down a relationship between the different enthalpy values, and that would be delta H1 plus delta H2 is equal to delta H3, all right? So that's basically the relationship between these three enthalpy values based on this setup right here, all right? Another way of looking at this, and this will become important when we actually do some problem solving, is that you can write down A going to B, and delta H1 would be the value for that enthalpy change, and then going from B to C, the enthalpy change would be delta H2. So if you add these two equations together, if you recall, if you have identical items on both sides, then you can cancel them out, which in this case would be the intermediate B. So therefore, going from A to C would be the sum of delta H1 plus delta H2, which would be equal to delta H3. So this is another way of basically showing you the same thing, all right? So that's basically what Hess's law says. Hess's law basically says that if you go from one reactant to a product through one step or several steps, the total enthalpy change is going to be the same. And this is very important because as stated here in this slide here, no, I'm sorry, this slide here. In fact, let me go to full screen. As stated here, some reactions cannot be carried out as written, all right? And that's very important because sometimes there's some reactions which cannot be carried out for pretty much practical reasons, all right? And therefore, if you want to find the delta H value, the change in enthalpy value for those reactions, then you'd have to use Hess's law along with other related reactions in order to figure out what the enthalpy change of that reaction is. And let me just say, going back to this right here, going back to this right here, it's very important that you recognize that this relationship is basically a conservation of energy or first law of thermodynamics law, all right? Basically what they're saying is that energy cannot be created nor destroyed, and in this particular case, the energy we're talking about is enthalpy, right? So basically what they're saying is that going from A to B to C is the same as going from A to C in terms of enthalpy changes, all right? So there's no loss or gain of energy in the form of heat, whether or not you're going directly from A to C or going from A to C through an intermediate or more than one intermediate, all right? Okay, so let me go back to the PowerPoint here. And in this case here, we'll be looking at an actual example. If you look at the reaction between carbon and oxygen, right, to form carbon monoxide, even though we can write an equation for this reaction and we know that this reaction can occur, it's very difficult to actually carry out this reaction in practice to get only carbon monoxide. And the reason why is because carbon monoxide itself will react with oxygen to form carbon dioxide. So in other words, let me go back to my writing pad here. So in other words, even though we know that carbon solid will react with oxygen to form carbon monoxide gas, you can also have the possibility of carbon monoxide gas reacting with another half mole of oxygen to form carbon dioxide. So the point is that it's very difficult to stop the reaction at this stage because as long as you have more oxygen present, then the carbon monoxide formed in the first step will react with any more oxygen present to form carbon dioxide, right? So therefore, it's very difficult to determine the delta H value for the first reaction experimentally. Now, it's easier to find the delta H for this reaction, and it is also easier to find the delta H for the reaction between carbon solid and oxygen to form carbon dioxide gas, all right? So basically, if we know this value, here and this value here, we can determine the enthalpy change for the reaction for which it's very difficult to determine delta H experimentally. So I think I have a slide which actually shows you how we can do that right here, all right? So this diagram here is what we call an enthalpy diagram. So we're starting with carbon and oxygen here. And when carbon reacts with oxygen, half a mole of oxygen, it forms carbon monoxide, right? And then that carbon monoxide will react with another half mole of oxygen to form carbon dioxide. As I said before, it is very, relatively speaking, easy to determine the enthalpy change going from carbon monoxide to carbon dioxide. And it's also relatively easy to determine the enthalpy change going from carbon and oxygen to carbon dioxide. In fact, the values are given right here. For the conversion of carbon monoxide to carbon dioxide, the enthalpy change is minus 283.0. And to go from carbon to carbon dioxide, the enthalpy change here is minus 393.5. So we can easily find out what the enthalpy change, which is labeled A here, for the reaction where carbon monoxide is formed from carbon. Because as we can see in this diagram, delta HA, which is for the first step, plus delta HB, which is for the second step, would give delta HC, which is for the overall step. So therefore, to find this value, basically all we have to do is find the difference between minus 393.5 and minus 283.0, and that will give you the delta H value for for the formation of carbon monoxide. In fact, let me do that right now. So basically, it's minus 393.5 minus 283.0, and according to my calculation, the answer here is equal to minus 110. Let me write it here. So the value here would be minus 110.5, minus 110.5 kilojoules, all right? So that's basically how we can calculate the enthalpy change of a particular reaction, which in practice would be difficult to perform and determine based on the enthalpy changes of other related reactions, all right? Let me show you another way to do this, because this will become important when we get to the example on the next slide. So what I'm going to do is, let me write down some values here just so that I have things organized. So, okay, so what I'm going to do is show you another way of doing this. So let me, okay, what did I do wrong here? You know what, let me just get out of this here, and let me go to my writing pad here. Let me get rid of all this here, and let me show you how to do this. So, to go from, to go from CO gas plus half O2 gas to get to CO2 gas, the delta H value for that would be equal to minus 283.0 kilojoules. And then to go from C solid plus O2 gas to give you CO2, delta H is equal to minus 393.5 kilojoules. Okay, so the problem is, how would we determine this one, the enthalpy change going from carbon solid plus half a mole of oxygen gas to get CO2? So remember, this reaction here is very difficult to, I'm sorry, not CO2, CO. Let me erase this here. This reaction here in practice is very difficult for the reasons I mentioned before, because once a carbon monoxide is produced, it will react again with oxygen to form carbon dioxide. So the aim is to determine the enthalpy change of this reaction based on the values and the equations given below. So what I would do is I would start off with this equation here, and I would compare it to this one. And I'll notice that the carbon monoxide here is on the right, but it's on the left in this equation. So what I would do is turn this around. Now, if I turn this around, right, if I make the products the reactants and the reactants the products, the sign would have to change, right? So when I turn it around, I will get CO2 gas to form CO gas plus half O2 gas, and delta H for that would be equal to plus 283.0 kilojoules, all right? Now, what I would do next is compare this equation to the first equation, and I'll notice that what they have in common is that they both have carbon by itself on the left side. So what I'll do is leave it as it is, and then what I will do next is add those two equations together. I'm going to add this equation to this equation, and what will cancel out, of course, would be the carbon dioxide, right? And let me see here. What would be the result? Oh, and by the way, this half mole of oxygen here will cancel out with half mole of oxygen here, leaving behind half mole here. So the result would be C solid plus half O2 gas to give CO gas, right? And it turns out that this equation here is the same thing as this equation here, which means that the delta H value here would be the sum of these two numbers, right? So basically, you're going to get 283.0 minus 393.5, and that will give you the same answer I got earlier, which is delta H for this reaction is equal to minus 110.5, minus 110.5. All right? So that's basically how we would solve a problem where you're given these two equations here. Initially, you're given this equation, and you're asked to determine the enthalpy change of that equation based on the delta H values for the first two equations given. Now, this is a relatively simple problem. So what I'm about to go to next is a more complex problem, but I'm going to stop this video here.